Hello friends. So in the previous video we have actually seen the inverted induction motor, and this video is actually a small correction which I have to make, which a small mistake I had actually made in the previous video. So this video will be a correction for that, and before starting this video I would like to thank Mr. Urvish Patel, who actually pointed out this mistake which I had made. So Urvish Patel, I am very thankful to you that you have found out this particular mistake which would have gotten unnoticed actually. And this is one thing which I like of you people, that whenever there is some mistake you people point out that, and which gives me an opportunity to understand that I have to be more careful while putting out these videos, and also this helps me to revise the concepts once again. And in fact I had spent some time with my friend discussing all these topics, and that was also on a nostalgic line where we were discussing how we used to prepare when we were preparing for these competitive exams, etc. So thank you Urvish, you have given a lot of you brought out a lot of memories for me also. So anyway, with all that, we will just see what is the mistake that I had done in the previous video. So the mistake was in this particular topic, that is the speed of the rotor field with respect to the rotor. That is, you know that the rotor field is going to produce a rotor field ns, and it's going to rotate in this direction. And I've told you the rotor itself will rotate in the opposite direction, right? So now we have to find the speed of the rotor field with respect to the rotor. Okay, so we'll just draw the diagram once again. So for example, this is the rotor structure, and you are supplying three-phase currents to the rotor, right, in the inverted induction motor case. So this, let's assume that it is rotating with the speed of ns. This rotating magnetic field is rotating with the speed of ns, and this rotor itself is rotating at the speed of nm. Okay, so what we have to find here is that the speed of the rotor rotating magnetic field with respect to, not the stator, with respect to the rotor, that is between these two. So here we are having our stator conductors also, and the stator conductors are stationary. Okay, so I've already told you, when for example you are having two people which are one person is walking v1 like this, and the other person in the opposite direction, he is working with the speed v2. So when you tell that what is the relative speed between these two, we tell that is v1 plus v2. But this v1 and v2 are with respect to a stationary observer, right? When I tell that the person 1 is walking with the speed v1, it is with respect to this stationary observer. And when I tell that the person 2 is walking with the speed v2, it is with respect to this stationary observer. So v1 and v2 are with respect to the stationary observer. So here also we have to define it like that. So the speed of the rotor rotating magnetic field with respect to the rotor will be equal to the speed of the rotor rotating magnetic field with respect to a stationary object, and in this case the stationary object is the stator. So it will be speed of the rotor rotating magnetic field with respect to the stator. Okay, so that is the first component, plus the rotor case. So the speed of the rotor with respect to the stator. Okay, so we have seen that the speed of the rotor rotating magnetic field with respect to the stator, what it will be. So if you are sitting here, this magnetic field is moving in the clockwise direction, in this anti-clockwise direction, and the rotor itself is moving in the opposite direction, that is the clockwise direction. So with respect to this person here, with respect to the stator conductor, the speed that the rotor magnetic field will have ns minus nm. So we have seen that in the previous video, right? So if you have not seen that, please go and see that. So this is the concept here. I have explained it in very detail in the previous video. So the speed of the rotor rotating magnetic field with respect to the stator will be ns minus nm, right? And what is the speed of the rotor with respect to the stator? It will be nm, right? It is the shaft speed. So with respect to the stator, the rotor speed will be nm. So it will be plus nm here. So this nm and this nm will go. So this value will be equal to ns. So this is the mistake I made here. So in the previous video I told it is ns plus nm. It is not ns plus nm. It is just ns. Okay. So the speed of the rotor rotating magnetic field with respect to the rotor, not the stator, with respect to the rotor will be equal to ns. Okay, so with this let us derive some more cases here. So the next thing that we have to derive is you know that, see, in the normal induction motor I have told you the stator magnetic field and the rotor magnetic field are stationary with respect to each other, right? Both rotate at the speed of ns with respect to the stator. the stator speed, stator rotating magnetic field with respect to stator is ns, and the rotor rotating magnetic field with respect to the stator is also ns. So that is why I told you how we can do all this phasor analysis and all, because these both are stationary with respect to each other. Now if this induction motor is also producing a torque, that same thing should hold. Okay, so in this case the speeds might not be ns, it might be something else. Okay, so first we will find the speed of the stator magnetic field, with respect to the stator conductors, with respect to stator. So that will be equal to 120 F stator divided by P, and F stator we have already seen in the previous video, which is equal to S into F electrical, right? So I can substitute that here. So 120 into S into F electrical divided by P. So 120 F electrical divided by P is nothing but ns, right? So this will be equal to S into ns. So 120 F electrical divided by P is ns. So the speed of the stator magnetic field with respect to stator is S into ns. Now in a normal induction motor, the speed of the stator magnetic field with respect to the stator is only ns value, because in that case you are giving the supply to the stator. In this case we are giving supply to the rotor and you are shorting out the stator conductors. Okay, so this is only valid for this particular type of motor. Next is the speed of the rotor magnetic field, with respect to stator. So this we have already seen, right? The speed of the rotor magnetic field with respect to stator, speed of the rotor magnetic field with respect to stator is ns minus nm. Now you know that the slip ns is equal to ns minus nm divided by ns. It's a basic relation. So ns minus nm will be equal to s into ns, right? So this is also equal to s into ns. So see, the speed of the stator rotating magnetic field with respect to stator is s into ns, and the speed of the rotor magnetic field with respect to stator is also equal to s into ns. Okay, so these both magnetic fields are stationary with respect to each other, and this is very important. And these are not only stationary, you should have to remember that they are rotating, okay, but they are stationary with respect to each other. Okay, that is the important point, and that is very much required for the torque production of an induction motor. Okay, so that is a small mistake which I have made here. So just watch the previous video, and at this particular point when I am explaining speed of the rotor field with respect to rotor, I have written it as ns plus nm. It is not ns plus nm, it is just the value of equal to ns. Okay, so that I have explained here. So again, I would like to thank Urvish Patel for pointing out this mistake. So till I see in the next video, it's me Varun signing off, and have a great day. Thank you.